Okay, so in the last video we went over how to create a sprite, how to use PF heights to make images. I think we made a rather convincing little group of buildings and a smiley face. Now I've sped the smiley face up a little bit, and so he's back to that normal speed as if it was one frame. Okay, and really what the purpose was for that video was to show that you can make a setup video, like a setup program, so that when you go to make a game, the presets for that kernel that you're using are already present. You don't have to type out every variable because you're always going to be using those same variables. You don't have to type out everything for your sprites, so you have a little blank slate to work from. You don't have to type out your whole play field. There'll already be a blank play field there to use, and that changes based on which kernel you've decided to use. Now, one of the best things you can do when you're going to program a game in Visual Basic is have the manual ready to open up. They have an HTML manual. It's offline, and you can just, click what you want to read about, and it's pretty intuitive. There are some hyperlinks in it that will try to go online, and so if you're not online, it's not going to go to those hyperlinks, but there's really not too much external information that's absolutely necessary. You get the bulk of what you need to know in the manual that it comes with. So let's go ahead and take a look at the manual. Okay. It looks like my camera is slightly off center here. Let's see if I can get as much of that in there as possible. Okay, so if you can see this, we have 2K, 4K, 8K, 16K, 32K banks, color chart. The color chart here is interesting. Now it's a little different than the color chart that pops up when you access your color chart from the TIA palette. This is your color chart from the TIA palette. And these are gross approximations of the colors because the colors are based on luminance. With the Atari, it's a different beast altogether on the TV screen. And so you can see here that the most available colors are with NTSC, 128 unique colors. They're more like shades. And then 104 with PAL, and 8 unique colors with CCAM. Okay, so suppose I'm done looking at colors, I want to back up. Now I'm back here at this, and you just click whatever you want to learn about here. You can add assembly language, a little bit about ASM. Here's your audio controls, background colors, a ball, how to make the ball wider. Use Control PF, and then how to use numbers to change the width of the ball, right? Bitwise, logical operators, Boolean operators. We've got colors for your background and your players and your play field. How to debug for cycles. The cycle count is how many things, how many calculations, processes can be done before the screen must be drawn. Okay, the Atari did something that they called in its day racing the beam, where the amount of time that the processor has to figure everything out is the amount of time between drawn frames, which is no time at all. It's no time at all. So now in later systems, they would have the processor basically halt the screen and then gather data, then draw the data on the screen, which is what the tile-based and sprite-based systems later on would do. And that was obviously far more efficient had more control over color and brightness in certain aspects. The Atari is crude in how it draws graphics on the screen. It's essentially just making broken lines that go from left to right, or they go across the screen, and then you can chop those lines up to form rows of color. That's really all it's doing, is chopping up rows of color and then stacking them. And how much it can show on the screen is, by comparison, not much, right? This was all for Pong. So when Atari was, this is my take on it, okay? When Atari was making this system, they were going to make a Pong system, just another Pong system. And someone said, well, if we make cartridges, then people can buy the cartridges, that's additional money, and then the cartridge can go in the system. And they said, okay, well, we'll just have lots of variations of Pong. But then someone said, okay, well, if we can manipulate the code to make more variety in the games, then we can actually come out with some different programs for this. So they said, okay, let's make some different programs. Then they came out with things like Combat. Now, if you look at Combat, it's a great example of what the hardware was meant to do. Okay, it's meant to make two movable player characters. It's meant to have a graphical playfield kind of image. Basically, it's just an arena. It's a squared playing field. Okay, it can have a ball that goes around the screen. It can also have a ball that is released from a player character, or what they call a missile. Okay, so you get two missiles, two player characters, a play field, and a ball. It can also keep score. All of this was for Pong. It's so you could have a Pong paddle that moves, a ball that is bounced between the Pong paddles, possibly some type of ball that can be more than one or one from a paddle, and a scorekeeping program. Okay, so then someone said, okay, we have serious limitations here. The system can only show so much, and we want to try to make some games. So if I remember correctly, what I read was that they were coming up with chess, which is a great departure from Pong, right? And they were like, we can't do this because it just takes too much math and calculations and stuff for this to be a decent chess game. So someone said, okay, well, what if we take a ROM, a read-only memory chip, and break it into banks? And then we have the system switch between the banks so we can fit more data on one ROM chip. That's when bank switching was invented, so to speak. Now, they figured out algorithms and math so that they didn't have to do bank switching for chess. I think they ended up making it without, but then bank switching became a reality. So then an 8 kilobyte game, which would be, I guess, 2 chunks of 4 kilobytes, which is 2 banks. Later, a 16 kilobyte game, which would be 4 chunks of 4 kilobytes, and then a 32 kilobyte. Only a couple of 32 kilobyte games were ever made for the 2600. The games I make are 32 kilobyte using 8 4K banks that switch with bank switching. Bank switching through Visual Batari Basic is not complicated. It's just you name the banks, and if you're going to a bank, you say which bank you're going to. In some cases in the code, if you are using Go subs, which are subroutines that leave to gather data, then return to the main routine, if you're leaving the bank to get the data, you'll want to say other bank at the end of the Go sub. And so there are little attentions to detail you'll want to pay attention to when you're working with more than one bank, but bank switching should not be a deterrent. You shouldn't be like, oh, bank switching's too hard, I don't want to make a bank switching game. Because with Visual Batari Basic, it's exceedingly easy to program in bank switching. You kind of want to. Unless you're in a 10 line of code contest and you're stuck with one bank, then you should be using as many banks as you can. I recommend 32K just because it's the easiest, and from what I understand, it's the easiest to get chips for. Like the biggest common chip that you can just put on an Atari PCB and get it to do stuff is a 32 kilobyte. If you're getting bigger than that, you're getting into some more fancy chips that might be more expensive or harder to get. So you can have mass-produced PCBs that will take the 32K chip. You can get blank or erasable EPROMs. An EPROM is an erasable, programmable, read-only memory chip. They also have EPROMs. An EPROM is an electronically erasable, programmable, read-only memory chip, meaning that the data on it can be erased through a program. But then EPROMs are windowed. A windowed EPROM is an erasable, programmable, read-only memory chip that through ultraviolet bombardment has its data erased. And then I have an ultraviolet bombardment chamber, just a little chamber. You put chips in it and it zaps them for about a half hour or whatever, and then completely erases the chip. And it works. People say they're crude or possibly not functional. They work. I haven't had any failures with my ultraviolet bombardment chamber for erasing EPROMs. Also, you can just set one on a windowsill and apparently, supposedly, the sun will erase the chip through its window. That's why you put a sticker over the window of an EPROM so that it won't be erased. And those are some, relatively inexpensive, and it's the largest size to comfortably program with Visual Batari Basic as far as I know. Now, with the graphics, you're stuck in just under 4 kilobytes of room for graphics, and it's all stored in the 8th bank. Okay, with programming, that leaves you 7 banks with 4 kilobytes each, which ends up being quite a lot of room for programming. So me, I'm a sloppy, eccentric programmer. There were people on the forum 10 plus years ago that would constantly say, let me see your code because I know I can make it smaller, I can refine it, I can make it more efficient. These guys who, maybe they're not creative enough to come up with a video game, but they're certainly nerdy and mathematical enough to reduce your code and make it more efficient and make it faster. Well, for me, I just don't care. What I care about is really simple. I want to get the graphics on the screen so you can move them around and interact. That's all. So I do things for efficiency, certainly, and you should, especially if you're exceeding the cycle count. But efficiency is not my primary driving force of programming. Making creative, colorful, fun, functional video games is my goal. It is not to make award-winning, miraculous, mathematical genius code that no one else can understand because of algorithms or something. I'm not interested in that. So BASIC is good for that. You've got your BASIC is easy. It was meant to be an instructional code set that anyone could learn, with simplified commands that anyone can learn to use so that a program could be made quickly. It has never been mathematically efficient when compared to anything low level. It is a high level code. Now, when we say low and high, quite regularly low is bad and high is good. Right? So if something has a high rating, that means it's good. If it has a low rating, that means it's bad. If I say somebody is high on my totem pole, that means good. If I say they're high on my list, that means it's good. If I say they're low, just saying someone is low, that's bad. That person is low. That is the opposite in programming. In programming, if you say low-level code, that means that the code is skirting the surface of machine interaction. That's as efficient as code can possibly be. So low-level code is assembly which are mnemonics that are machine language. That's as low as you can get next to binary interaction. Machine language in its mnemonics becomes the lowest possible interactive level, which is the fastest, most efficient interaction with the machine. High-level code has a barrier of language that converts it to binary or converts it to assembly or both. Everything is converted to binary, which is ones and zeros, which is the language of the processor. Okay? Now, when you're dealing with a processor, there are limits to what a processor can do all at once. And I've said this in other videos, and this is dense. This is just to conceptualize what you're doing. So with 8 bits, it's easy to conceptualize what's going on. Think of 8 light switches and how many different variations of off and on you can have with 8 different light switches. There are 256 possible combinations of off or on with 8 light switches. That's how an 8-bit computer processor is. Now, in one cycle or one active use of that processor is your 256 possible combinations. So what ends up happening is patterns are generated that create responses. And so really it doesn't know I'm making a picture of Popeye eating spinach. It doesn't know I'm making Pac-Man eating pellets. It doesn't know I'm making clouds that move across the sky. It doesn't know I've made a tank that shoots at another tank. It has no idea that I'm keeping score of how many milkshakes Taz eats. You know, it doesn't know any of that. All it gets is ones and zeros, and then the system knows to put bright dots of colors on the screen with combinations of these ones and zeros. Okay, so when you get into 16-bit, you're dealing with many, many tens of thousands of possible combinations. When it comes to 32-bit, you're getting into possibly millions and millions of combinations with 32 bits, 32 different light switches, right? When you get into 64 bits, you're dealing with billions of possible combinations. So these are like, they're mathematical oddities. How many different calculations and how many possible outcomes that can happen the higher up you go. So 8 bits is very, very crude and simple, and it's not nearly as complicated as 16, 32, or 64-bit operations. So maybe it's a little bit easier. So if I'm dedicating a variable to count up 1 every time a loop is created in my code, the highest number that variable can reach, counting 0 as a numeral, is 255, because it's a bit operation, saying I've got 8 bits to work with. I'm basically flipping light switches until all the combinations of the light switch are done, and the variable is having a numeric value assigned to every different assortment of up and down switches. Okay, so that's way more complex than what anybody needs to understand to use this code. For the code to work, all you really need to know is that once you've reached 255, the next number will be 0. It's going to reach that and then go, okay, I'm done with numbers that I can use. I'm going back to 0. Okay? Now, this affects how random numbers are generated because there are less random possibilities. This affects how the timing of the system is. For instance, if you want to make a real-time second-per-second counting clock, that's possible, but you're dealing with fine-tuning the timing of the processes and of variables. Okay, so you could in effect get a clean atomic digital timer and then adjust variables until it's counting as close to 1 second as possible. And there's probably some variables, like not like math variables, but like there are some variables in the machine itself that might cause variety there. So with electricity and the responsiveness of resistors and the oscillation and just all those things might make it, just like with a clock on your VCR, and it seems to always slow down or it seems to always speed up, you're going to deal with variance. But it is possible. You can use this to do a lot of different things. Okay, so when making these different presets, I'm doing it so that when I want to program a video game, I just grab that preset, I put it up on the screen. What I'll often do is I'll decide how I'm going to approach the creation of the game. And I have either multi-sprite or standard. I have standard using a super chip, which I kind of avoid now because of the cost of the chip. Or I have standard using PF heights. I might use standard with no blank lines, but I'll likely just use either standard with PF heights, which I have a lot of success with, or I'll use the multi-sprite kernel as it is. Okay, so let's look at the strengths of each of those. Okay, so now my startup for multi-sprite is, of course, it's different than the standard kernel because it uses sprites differently. Okay, the standard kernel, which is based on the simple, normal functionality of the Atari video game system, where it gives you 2 sprites, 2 missiles, 1 ball, 1 playfield, and a background color, and a score keeper. Okay, and so in the standard kernel, without any extra things added to it, that's what you're going to get. And you get to manipulate those however you want. It seems pretty limiting, and to a degree it is. Now, to add more sprites, the multi-sprite kernel takes sprite 1, which is the second player sprite usually, and it makes several copies of it, okay? So that you can have 5 different sprites in addition to the player 0 sprite, which is usually player 1, the first one. So remember, in coding, 0 is a number. And 0 doesn't mean nothing, it's just like the starting point. Okay, so player 0 isn't no player, and it's not nothing, it's actually the first player. And player 1 isn't the first player, it's the second player. So welcome to a world of confusion. Now, some different changes, some things that are different about the multi-sprite kernel you want to pay attention to is it labels the new size registers for player 1 with this beginning little underline. Where my, if you can see that, I hope you can. I'm using some brightness here with a little more exposure to try to get my screen to be slightly brighter. So we'll see how this turns out after I'm done recording it. Hopefully you'll be able to see this better. So you have to make sure to put an underline before the new size 1 register, but if you notice the new size 2, 3, 4, and 5 do not need that. So anytime I'm controlling the size of a sprite, sprite 1 has to have this little underline in front of it. Okay? So does color. Color 1, call P1 here, also has to have that underline, but not 2, 3, 4, or 5. Okay? Now you still only have missile 1 and missile 0. As far as I know, this doesn't give you missile 2, 3, 4, or 5. It doesn't go that far. Now, one of the big strengths of the multi-sprite kernel is that you can adjust the height of the rows in your screen automatically. So where the PF heights kernel, or the PF heights addition to the standard kernel, I should say, allows you to control the individual width of 11 separate rows using the standard kernel, PF height, without an S, allows you to control the width of every row continually with your 88 rows or less. You can have 88, 86, 84, 82, and every group of rows you take off is less cycle counts that screen's going to take up. Okay, so the smaller your screen overall, probably the better. 80 or 82 or 84, maybe that's good. I usually use 88 or 86, maybe 84 if I want to really squish things down. Now, so here, and I'm just, this says Cockpit A because I was working on a spaceship game. This can say level 1A, whatever. Okay, PF height 3. What this means is that I will have 22 rows here. Now that means that if PF height is 1, then I'll have 44 rows. Okay, so the way PF height works lets you have thinner lines across the screen. Now if you'll notice, this is a 16 section wide playfield. That's because everything in the multi-sprite kernel is mirrored. So no matter what you draw, it's going to have a mirrored section to the right of it, and so everything's mirrored. And it's, well, if you like to draw things that are mirrored, then it's fun. Okay, but if you don't like to mirror things, it's just going to get in the way. There are ways to change it and to get around it with certain registers. I'll talk about that later though, but like it doesn't have to be mirrored. It actually can be doubled where it's two of the same screen right next to each other, but there's usually a gap in the center because the right side gap is now in the center of the screen. Also, there are certain ways to just have what's visible in the 16 rows with blank on the side. So there's some little creative things you can do that will make it not mirrored, but just out of the box, Multisprite is mirrored 16 rows. You get your 32 rows. Also, it's stored in your graphical ROM space. And so even though you get more sprites to use, and those are going to use up space, your background is also using up space. Whereas with the standard kernel, the playfield is not stored that way. The playfield data itself is treated like normal data in the bank. Things that act on the playfield, like PF heights or the definitions of the rows of color, those will take up additional space. So even though you have less sprites with the standard kernel, you have more graphical space in that 8th bank for the sprites that you're using. Okay, so let's look at a couple of examples of games that are using these two different kernels that I'm working on, and we'll see some of the effects that are happening with the use of those kernels and what you might be able to expect to be able to achieve with the limitations and the strengths of the different kernels. Okay, so now I'm going to run through now. This is going to end up being kind of a unintentional advertisement for all the projects I'm working on just by showing this stuff, but this is going to be where I show a project I'm working on, either a completed game or a work in progress. Most of them are works in progress. And then I'm going to explain how I'm doing what I'm doing on the screen with the strengths or the weaknesses of that specific kernel. Okay? Now, so the first one I'm going to show is a Ghostbusters game I'm working on called Ghosts or Bust. It's based off of the Commodore 64, Atari 8-bit computer, and other original Ghostbusters video game. And this is a work in progress. Okay, now it uses the Multisprite kernel, 32K, and nothing else. Just like that's what I'm starting with. And we're going to show that game. Okay, now, so this screen is done using one layer of the higher resolution PF height multi-sprite screen. So it is mirrored. The thin lines are from that higher resolution. Now, because the sprites are being generated on the second lower resolution screen, I can have sprites moving on this screen. But usually we'll have problems with the highest resolution PF height screen mixed with sprites. Now, so by layering them, I get the additional colors, I get the different, and it is mirrored. So if you look at the buildings, if you just look at one side of the screen, you can see that this is the same as this, this is the same as this, and so on. This is the same as this, this is the same as this. Now, in the original Atari 2600 version of this game, the ghosts only came up from the bottom of the screen, whereas in the computer versions, they came from all four corners of the screen, working their way to a center point, which is the building where Zool is. I wanted to have the four different ghosts moving from each side of the screen like the original. So that's what we've got here. When you run into the ghosts, it briefly stops them, which keeps the PKE meter from going up so fast. I've got the phone here lighting up for the place where the ghost is. So I'm going to hit the button on that one. Now I have the Ecto 1 driving scene. This is a 3-colored sprite, red, blue, and white. Don't ask me how I ended up blending colors to get those 3 different colors, because that took a lot of experimentation. I'm actually speeding up to keep it from going to the next screen, because the way I've programmed this for testing purposes, if you accelerate the car, it won't go to the next screen. You have to go the normal speed. I have a multicolored ghost sprite, which you can suck into the ghost vacuum if you get it. Okay, and it can move left and right. This is a fake animation kind of screen where 2 or 3 different screens are played to depict the lines of the street moving, which will, all of this will probably be simplified later to free up more memory for graphics. Okay, I'm going to go ahead and slow down now, and then it's going to reach the first building. Okay, here's the first building. It's got Slimer, and he is a multicolored sprite. He's got 2 or 3 colors going on there. It's got Winston Zeddemore on the right side, Peter Venkman on the left side. It's got the tables. This is to depict the ballroom scene where they first encounter Slimer in a way where they can catch him, because this was after Peter got slimed, and they're creating lots of noise and property damage and stuff. This is before they give him the bill that he refuses to pay, and then they tell him that they can just let the ghost right back in. He says no, 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 and then he pays them. So this is a mirrored image. Again, everything in Multisprite's mirrored. So this is using a relatively high resolution Multisprite display. There are no visible lines through things in Multisprite, so you don't have to do the no blank lines or things like that. So it ends up making a really nice picture. I like it a lot. So again, though, if I cover up half of this screen, you can see that everything is the same. See, like from there over, it's mirrored. Okay? And what the goal here is, and I'm going to completely change this game. I'm going to add the text kernel so that we can have words. All my games are going to have text kernel from now on. The ghost will move around and then possibly either try to escape or throw things at you. I want him to throw things at you, so it will be different than the original game. And based on the building that the ghost is in will be what the ghost is throwing at you. I made all kinds of different things for the ghost to throw. And so like if it's an apartment building, then it will throw Nintendos and Nintendo cartridges and fish bowls at you and stuff like that. If it's a hospital, then it'll throw syringes and bags of blood and bedpans at you. Things like that, okay? I came up with roughly 17 to 20 different backgrounds. Of course, not all of those can be in the game. And I came up with an end scene with Zool and Gozer and Vince Glortho and all 4 Ghostbusters with their proton packs and stuff. So this has all the graphics done. It has most of the coding. It just needs the animation, but I want more graphics. And so what I'll probably have to do is lower the resolution slightly of the backgrounds so I can fit more backgrounds. I don't know, it might have a complete overhaul once I put the text kernel in there for the words, because I want them to say things, and I want just more, right? So this is a multi-sprite kernel mock-up of a video game, okay? So next let's show this one, Cute Kong. This is another multi-sprite kernel game, 32K. And now the question here was, how do I get a Donkey Kong game but still use the mirroring? Okay, because I wanted multi-sprite so I could have lots and lots of barrels or flame monsters or whatever the bad guy is, right? I also wanted to have a very Donkey Kong-like type of interaction. Now, the original 2600 game didn't have the flaming barrel, didn't have the fire chasing after you. It didn't have, in my opinion, a very good-looking Donkey Kong or King Kong bad guy. I wanted the girl to be really cute. Okay, so we've got the girl being held by the gorilla. She's beating on his arms and shaking and trying to get loose. We've got a King Kong gorilla, so he's not really Donkey Kong. He's more like King Kong. We've got the barrel that is ready to blow up and have the flame chasing you. We've got Jumpman. Okay, so I start the game, and I'm going to race these barrels here. Once it hits that, boom, then we've got the flame coming after you. Okay. I haven't programmed the hammer yet. This will be the hammer, jumping up and grabbing the hammer. I have to get these guys out of my way so I can keep going. Now that area is blocked. Oh, he got me. Almost made it. I was right there. You can see the girl's like calling for help. Okay, the gorilla is animated, and I wanted kind of a pastel, kind of a cute color scheme. My goal was to make a series of games called Cute. Like I wanted Cute Beach, which is a volleyball game, Cute Kong, maybe like Cute Burger, which is Burger Time, Cute Sailor, which is Popeye, and just add these extra elements of cuteness to every game. Okay, so how is this multi-sprite? Well, we don't have the inclined sections. Everything is a straight line, right? So he's not going like up a slanted, broken beam, floor beam. He's actually going across flat floor beams. But if you notice, the way the ladders are broken make it like the ascending parts of the original game, right? So, crap. Having some sinus. The gorilla is mirrored because it's part of the background. The bar on the right side here is actually a missile to add for that little climbing part. So that would otherwise be broken because it's actually mirrored here. This is a mirrored broken ladder, working ladder, and then fixed ladder. And then here we have the same exact thing. We have a working ladder because of a missile, which would be a broken ladder mirrored. And what this does is it funnels you so that you're forced to go across this bottom part to this ladder. Then you're here, you can't go there, you can't go here or here, you have to go here. Then once you're here, you can go up this one or up this one, and then once you're here, you only have this one. So it's forcing you to take this long pathway to get up to this point, right? And the flame blocks off the descent. So you can't, after the flame reaches it, you can't go get the hammer, you can't descend down the ladders. And that makes it a little bit different, obviously, than the 2600 version of the game. I wanted a more complex, better looking version for the 2600. But this is that multi-sprite kernel where everything's mirrored and there's lots of different sprites on the screen. Okay. Now here we have the game that I finished and was sold, Yeet Fighter. This uses the standard kernel and PF heights. Okay, let's go ahead and see if I can't pick a character here. There we go. This has lots of songs, has Street Fighter II style fighting moves, projectiles, 3 colored sprites at least, has a timer, it has round counters, has different backgrounds. I think I'd like to put better music in it. I think with the sequel to this game, I'm going for much better music. What I did was some of the songs from my first game, I went ahead and added to this, and I sped them up. But the first song was made a while ago when I was doing different musical arrangements using the noise processor for this system. So I liked it, so I went ahead and used it for the song, the title song, which I think is really good. Took me out there. Okay, so let's restart. And I'll just pick, this is the versus mode. Okay, so if we look at this, we've got an animated background. The boxes are done with large chunks of PF Heights boxes. Several different tops are combined to create the animated propeller. The white line is one large bar of PF heights. Each of these characters is essentially just a palm paddle. The kicks and punches are missiles. So his foot is a missile, his arm is a missile. It's two layered missiles to create colors. The weapon there, that's a sprite that is added to be a third sprite. That's why she's flashing there when it does that, is because there's a third sprite being added. That's his foot kick. Okay. That's her flying attack. Which is done like a dragon uppercut. There, that's like a dragon uppercut. There it was. Nice flying knee. Lots of moves. There's lots of moves in this. Okay. So this is the standard kernel using PF heights to control the widths of every one of the 11 rows in the playfield. Some combining of rows, combining of sprites. Okay. Alright, now this one is another multi-sprite kernel game that I'm working on. Start this out. You can see there's words at the bottom. Now you can see that every screen is mirrored. Okay, everything is mirrored. The character is layered, the backgrounds are layered to create 3 colors, plus there's the background colors. So here we have brown and green. They're combined to create this reddish color, and then we have another shade of green as the playfield. The character is 2 different sprites layered to create 3 colors. So with multi-sprite, we can see here this is a mirroring to create this little town. There's a gap here in the fence, and you can see that both buildings are the same. Now at one point though, one of the buildings is actually different, and that's with a little trick where you can actually make it do 2 copies rather than mirror. Now I'm trying to do creative things that haven't been done on the Atari yet, but if you just want to make a single colored sprite or a rows of color sprite, that's easy. That's very simple. If you want to make a single colored or different rows of color background, that's all stuff that's been seen on the Atari that can be done using Visual Atari Basic. Using the methods that I use, you could end up with some flashing or flickering or exceeding the cycle count, running out of ROM space really fast. So this takes some fine tuning and tweaking of things to get it to work. So this is not something where you just decide to combine colors and everything works. You have to usually use darker colors and layer them. You have to test it on real hardware to make sure it doesn't flash or flicker too much. Now today most people probably play in emulation, and so this is what you would get if you used a computer emulator to play this game. Okay, so let's look at another one. Okay, here we have Multisprite with text. Now you can see that the screen is mirrored, but I have sprites helping to make the screen look a little different on each side. Let's go ahead and pick wrestlers real quick. Okay. So the ring is mirrored. All the signs are sprites. The referee is a sprite. The wrestlers, the wrestler and the referee are created using two single color sprites layered to create a third color. So even though this might kind of give off the appearance of a two sprite kind of thing, like something the standard kernel can handle, to have lots of different sprites on the screen, I have to use the multi-sprite kernel. And because most of the time a wrestling ring is a mirrored image, that helps. So this is mirrored. Okay, let's take a look at another one. And you'll kind of see a theme here where a lot of my games use the multi-sprite kernel. That's just because I want more moving, animating, interactive images on my screen. I just want more. So here we have a sign that's a sprite with the flashing S. We have a cop car that has the flashing lights. The building is mirrored. We have our character, large sprite character moving. We have our zombie character. We have products on the walls or on the shelves there. I don't know if I can leave this screen. I guess I can see. No, not yet. This additional areas aren't programmed yet. And most of these are works in progress. So there's still a lot of work to be done before they're actually playable games. But these are proof of concept, and as long as I can cram in enough screens, these are what the Atari game will look like. Okay, so this is using Multisprite. Okay, here we have another one using Multisprite. So here it uses two joysticks. One controls the throttle and transformation. Now the multi-sprite kernel is used here just so I can have more sprites. The same effect with the moving ground animation and probably some of the clouds and stuff, that could be done in the standard kernel, but I couldn't have more graphics. So I want to have more. I want to have an enemy sprite or a couple of enemy sprites up on the screen, maybe some animations for missiles moving and gunshots and laser blasts and just lots of stuff. So again, the multi-sprite kernel is probably my most widely used kernel, and it's just more graphics. It's more costly in ROM space, but it's more graphics. Okay. And we'll look at one more, and this one uses PF heights. This one does not use the multi-sprite kernel. Okay. So this one has a lot of detail though, and that's because I'm using a lot of the single width PF heights layers. So the panels here and here, those have single thin single sprite layers. Some of the details on the chairs. I don't know how bright this is on the screen. I hope it's bright enough to see. The comm works, so as I move, the enemy ship goes on or off the screen. And now it's actually zoomed. The enemy ship is zoomed right now. It would probably look better if it wasn't zoomed in. Let's see. Using remarks in this to help me to remember. Maybe it's this. Let's see. There we go. Okay. So now we have the ship, the normal size that would be. And it matches up now with the comm reading. Now if I hit the button here, it shows my ship. This is done using PF heights, where the thinner sections of the ship, like what you see here at the saucer section, those are thin strips. It's lots of layering. Sprites are used for certain colors. It's just a combination of layered playfield graphics and sprites combined to create this. And I like it. I think it's cool. I think it's one of the coolest enterprise ships done on the Atari 2600. There's probably only one other one with strategic operations simulator. So going for a really good looking enterprise. And that's just all done using different widths of chunks of the playfield. So even though it does have lines present, I don't think it really shows that, you know, it's forced into that bracket where everything has lots of gaps and lines through it. It's more of a creation of wide chunks of color to create that. Okay. And this one does the same thing. Anywhere where there's a wide chunk of color, we're getting, this doesn't really look like it has lines forced through every layer of the graphics. I hope that's bright enough. Okay, so now we're going to look at, let's see, I don't know, actually that might be all of them, and only two. We have Space Navy here. That's a PF Heights with the standard kernel. We also have S&K, which is PF Heights with the standard kernel. All the other ones are using the multi-sprite kernel as to show kind of what can be done. So that was kind of a look into some of the ideas of what you can do facing those limitations. So having 5 sprites or 6 sprites on the screen helps a lot, but there are also some advantages to using the standard kernel. Like you can actually scroll the screen and move the screen around with the standard kernel a little bit more easily with just simple hardware commands. You can do layering of graphics, but also you can create several different, like what I do is I create 2 play fields for every one image, and that gives me layered graphics, but that could also give somebody 4 sprites if they're single colored or if they're color row sprites, just by doubling them up. You might get a little bit of a ghost-like effect or a shimmer effect, and a lot of times that's not even visible. It's not something that anyone would even see or think is a problem with it. It's when you're layering a whole bunch of things and you get a shimmer, like you get too many things moving at the same time, and that just happens with Atari games. You're going to see that also happens with Nintendo games. If there's too many sprites on one horizontal row, you'll get missing chunks of sprites and stuff and flickering. So that's not something that's exclusive to the Atari, but the Atari has a bigger problem with it because it doesn't really have like graphics processing stuff going on. It's just rows of colors slapped up on the screen. That's really all you're getting here. So just kind of a look into some of the ideas, what you can come up with using these kernels. Okay, in the next video, maybe we'll do a little bit more kind of instructional oriented material to try to maybe help somebody get an idea of what can be done using the Visual Batari Basic to create an Atari game. So hey, if you tolerated this, thanks for watching, and any comments are appreciated, and I really love that there's such a diverse and just a wide array of different kinds of home brews, especially with Atari, and people just coming up with all kinds of creative ideas for all these systems. And I really wish I had all the time in the world, all the energy in the world, and I could just come up with all these. I want all of these games to be a reality. I want it all to be real, so you can buy a cartridge or you can download it for your system. And so yeah, just in closing, let's go ahead and just show this one again, just for fun. So, thanks for watching.